Lu Kong and George's talk is titled Open Path versus Closed Path Gas Exchange Measurements. Lu Kong?
Thanks, Ashley. Good afternoon from LI-COR Bioscience here in Lincoln, Nebraska. It's nice to see you so many join the webinar today. Today we are going to discuss the open path and the closed path gas analyzer for eddy-covariance flux measurement. And we are going to focus on the advantage and the benefit using either one of the analyzer in the eddy flux measurement. And I will talk first on the open path, then George will discuss the closed path analyzer. Due to the half-hour timing limitation, our discussion will be on some highlights only regarding the two types of instrument without going into all the details. You are welcome to contact us after the webinar for further discussion. The Earth is getting warmer and warmer. No single day goes by without hearing from the news media on the topic such as global warming, climate change, sea level rising, carbon dioxide emission, carbon dioxide sequestration, carbon cycle research. As we all know that global warming or climate change mainly is due to the continuously rising of the atmosphere CO2 concentration since the Industrial Revolution at the end of the 18th century. Here we show a simplified global carbon cycle from a 2007 IPCC report. Our human beings every year dump about 6 gigaton carbon into the atmosphere from burning fossil fuel, cement production, and land use change such as deforestation. The ocean takes about 2 gigaton carbon each year, and the terrestrial ecosystem takes about 1 gigaton carbon. So every year the net increase in atmosphere carbon will be around 3 to 4 gigaton. And scientists want to know more detail on how much carbon is uptaken by the terrestrial ecosystem. As we show in these slides, for an ecosystem, carbon uptake is through the photosynthesis process, and the CO2 release through the plant respiration, soil respiration, and maybe erosion. Some carbon will be stored in the soil as organic material. To understand how environmental and biological variables, including radiation, temperature, precipitation, soil moisture, and the plant canopy size, mainly the leaf area index, control or regulate the carbon cycle process at the ecosystem level, research monitors long-term or all year round net carbon flux using the popular eddy-covariance method. This kind of information is necessary for large-scale modeling study. The eddy-covariance method measures the high frequency of vertical wind speed and CO2 density, then using the equation here to compute the flux. Basically, this method measures how much CO2 in the updraft air parcel, we call eddy, and how much CO2 in the downdraft air parcel, then average it over half hour. You will get the net CO2 flux exchange between the ecosystem and the atmosphere. In the turbulent air near the surface, eddy size vary quite a bit, but for flux measurement, it is sufficient if you have a wind speed sensor like sonic anemometer or CO2 analyzer with a 10 Hz response. Since higher frequency eddy faster than 10 Hz won't contribute to the net CO2 transport. So normally the login frequency for the eddy flux measurement is 10 Hz. Using the same method with the H2O analyzer and a fast temperature measurement, you can estimate sensible heat flux and the latent heat flux, as I showed in the equation above. Vertical wind speed W can be measured with a sonic anemometer. Quite few companies manufacture excellent sonic anemometer, like Campbell Scientific, Gill, Metec, RM Young. From a 3D sonic anemometer, we can get UVW and sonic temperature. In theory, we only need vertical wind speed to compute the flux, but 3D wind speed UVW are needed for the coordination rotation. So the mean vertical wind speed will be 0 during the half-hour averaging time to satisfy the requirement of air mass conservation. Sonic temperature can be used for sensible heat flux computation after converting the virtual temperature from sonic to real temperature. CO2 and H2O can be measured with either open-pass or closed-pass analyzer. Here I showed an open-pass CO2 and H2O analyzer, the LI-COR 7500. I also showed an example of 10 Hz vertical wind speed W and CO2 data from 10:40 a.m. on April 14, 2002, from an active grassland in California when I worked in Professor Dennis Baldacchi's group as a postdoc at UC Berkeley. Since grass was very active uptaking CO2 by photosynthesis, so when you have a positive W, means the eddy is moving upward. The eddy is from the grass canopy. The CO2 concentration was decreased. When you have a negative W, means you have a downward moving eddy. The analyzer sees a fresh air from above, so the CO2 is increased. The main advantage of the open-pass analyzer is the lower power consumption. The open-pass 7500 is designed for remote field site. The main advantage of open-pass analyzer is lower power consumption. For a LI-COR 7500 on the steady-state condition, it only needs about 10 watts. The whole flux sites, in which I showed here as example, including anemometer, data logging, and other various sensors, can operate with a solar panel. This will give you a huge flexibility to select location of your research sites when you don't have AC power. Other advantage for the open-pass analyzer: high speed, you can log in the data up to 40 Hz. High precision, the root mean square noise of only 0.11 ppm CO2 at 360 ppm ambient level, and 0.0047 ppt H2O at 10 Hz sampling frequency. And also, since there is no tubing needed, and it eliminates the delay, and also no tubing attenuation for CO2 and H2O signal. And this instrument also has excellent stability, and it's very good for a harsh environment. According to the Flux Net Office at Oak Ridge National Lab, as of March 31st, 2009, globally we have 576 towers to monitor CO2 and H2O flux over various ecosystems. The majority of the towers are using open-pass CO2 and H2O analyzer, the 7500. And one additional calculation of the eddy flux measurement when you're using open-pass gas analyzer is the density correction. We call WebPM and Luning correction, often referred to as WPI correction. Open-pass analyzer measures number density of CO2, which has a unit of micromole CO2 per cubic meter of air, not the mole fraction. So the number density will change if the number of CO2 molecules change in the sample air due to the uptake by the leaf or release from the respiration. This is what we want to measure, and this is what we want to know. But the number density will also change if the volume of the air expands or contracts due to the change in air temperature or due to the change in air moisture content. If you're using eddy-covariance method to measure carbon flux over a parking lot in a hot, dry summer, you will see a huge carbon uptake by the concrete if you don't apply WPI correction. This has been explained in theory and confirmed by experiments done by Ray Luning and J. Ham. We're not going to show all the details in the derivation of the WPI equation, but here is the final version. You might see some other version of this final equation in the literature. The W prime rho C prime is a raw flux, and the W prime rho V prime is a latent heat flux. That's a dilution from the water vapor. And the W prime T prime is the sensible heat flux term. That's a air expansion due to the sensible heat flux. And rho C is the CO2 number density. Rho A is a dry air density, rho V is a water vapor number density, T is air temperature, Ma is a dry air molecular weight, and Mv is a water vapor molecular weight, and Fc is a final flux. I show an example on this slide to see how big the magnitude of the WPL term as compared with the final flux. This dataset was from a grassland in the dry summer when all grass was senescence and the soil was almost oven dry. The soil volumetric moisture content was down to 3 to 4%. So all the available radiation energy partitioning into the sensible heat flux and only small portion of the latent heat flux LE. When you calculate the W prime rho C prime, you will see huge downward CO2 flux during the daytime, up to negative 20 micromolar CO2 per square meter per second. But after you apply the WPL term, very good respiration upward flux was observed, averaged around 0.5 micromolar per square meter per second. This lower respiration rate was consistent with chamber-based soil CO2 flux measurement. The WPL correction term has a sound physical explanation, and it is well accepted in the carbon flux community. It is not due to the instrument error or any kind of artifacts in the measurement. One should not look at the relative magnitude of the WPL term and the final flux term Fc. WPL correction term must be measured in order to have an accurate CO2 flux measurement. In fact, many scientists are starting to refer WPL correction term as a WPL term simply because it is not an error term. Since the optical path of the open path is open to the air, the analyzer will not properly operational, so during rain, snow, foggy weather condition, the data will be invalid. Therefore, if a study site has high precipitation or frequent foggy weather, a closed-path analyzer is preferred. My friend George will discuss the closed-path analyzer configuration.
Thank you, Lukong. Before we move on, there are a couple of good questions I'd like you to answer. The first question is, how often do you need to calibrate the LI-7500?
That's a good question, and we got a phone call from a customer and quite often. Normally, you need to calibrate the 7500 every month, and since it is used for the flux measurement, use the eddy-covariance technique, zero drift won't have any impact on the flux measurement. For example, 1% of the span drift will translate only 1% error in your flux value. The instrument is very stable, and it is often installed in the field without calibration for months and months.
Thank you, Lukong. The second question is, how often do you need to replace the internal chemical bottles?
We have two small chemical bottles inside the analyzer housing that keep the detector free of CO2 and water vapor. One is contains ascaride to remove the CO2. Another one is magnesium perchloride, removes the water vapor. Those two chemical bottles need replaced on an annual basis. You can buy this two chemical bottles from LI-COR. For a research site, it's very humid, like in a tropical area. Those bottles need replaced more often.
Great, thank you, Lukong. I encourage you to keep submitting your questions throughout this presentation. Lukong will be online to answer anything that might come up, and I'm going to turn the floor over now to George.
Thanks, Ashley. Lukong just told you about open path gas analyzers and their key principles and operation standards and field maintenance. Now let's switch gears and talk about closed path gas analyzers. We will review the key features and important moments of field operation for those sensors. Closed-path gas analyzers are well established and widely used to measure concentration and fluxes of CO2, water, methane, and other gases. When main principles of operations are recognized and proper care is taken during setup and data processing, closed-path analyzers provide highest quality of data. This has been proven over and over again by over 30 years of research by thousands of scientific groups. In this presentation, we'll touch upon key features of closed-path analyzers and on most important operation moments related to demanding fast applications, such as eddy-covariance flux measurements. We'll touch upon the most important points in the interest of time, and we go in the following sequence. First, we discuss principles of operation. Then we discuss key differences from open-path analyzers. Then we talk about how sample air is modified when it's pulled into the analyzer and how to correct for such modification. Then we also talk about key moments in setup and operation and in data processing and analysis. Then we summarize all the key points, and I'll talk to you about some news related to closed-path, open-path instruments at LI-COR. Closed-path gas analyzers can employ various technology of sensing gas. For example, non-dispersive infrared technology, as many standard analyzers use. They can also use single-line or narrow-band laser absorption approach as used by newer laser-based analyzers. They also can utilize gas chromatography, flame ionization spectrometry, and many other methods. They can be applied to slow or to fast techniques of measuring fluxes. Slow techniques usually refer to techniques requiring less than 5 Hz of data collection. Examples would be bone ratio method, gradient method, inverse flux calculation, and so on. The fast term usually refers to techniques requiring high precision concentration measurements with frequency above 5 or 10 Hz, such as eddy-covariance technique. And this later one would be the main focus for this presentation. Example of sensors used for slow techniques are CO2 gas analyzer LI-20 and CO2 and water gas analyzers LI-840, 6251, 6262, and the latest LI-7000. Out of those, the fast techniques only can be used with 6251, 6262, and 7000 because of requirements for high speed and high precision measurements. Closed-path gas analyzers have a number of advantages in fast techniques. They have minimal data loss due to precipitation and icing, minimal uncertainty associated with fast temperature fluctuations and related WebPM sensible heat flux term, possibility of outputting mixing ratio and avoiding using of WebPM learning term, no surface heating issues, possibility of automated calibration, and possibility of climate control. And we'll go through these features in more detail in the next few slides. Let's go to applications now. Applications for closed-path analyzers are very wide. Here are just 3 examples. The terrestrial application refers to flux networks, which employ 7000s and 6262s all over the world. The advantage of closed-path analyzers for this application is that the data collection is limited by sonic data during precipitation and not by the analyzer, the gas analyzer itself. Airborne applications refer to the instrument usually housed inside the aircraft and air is pulled into the sample cell. Such measurements taken over short periods of times, like hours, and used in inverse modeling and sometimes in direct eddy-covariance measurements of flux from airplane or helicopter. Oceanographic applications usually refer to CO2 and water flux measurements from the ocean and sea surfaces. And the advantage of closed-path analyzers there is that they're not susceptible to spray and rain and fog and salt deposits. when you measure directly from the ship or the boat. However, these measurements are challenging because of ship pinch and other movements which affect gyroscopic effects on the analyzer chopper wheels and other parts. The main principles of operation for closed path analyzers are pretty simple. The air sample goes through the tube and enters into the cell. And when it happens, air sample is of course affected by tube and the cell walls. So we need to understand and to compensate for these effects. At the bottom of this slide and at the bottom of few other slides, you will see the link which gives you more explanation and provides literature references for some of the points we discuss here. So you can write it down and just go to our web page and see it. How exactly sample is modified by the flow? Let's look into the details. The picture here demonstrates the usual setup of closed path analyzer. The air is sampled through the rain cup and some kind of filter. It goes through the tube, maybe to the bottom of the tower or to the middle of the tower. It usually has a water trap, and then it has a fine particle filter to prevent cell from getting dirty. Then it goes through the closed path cell and out to the pump. As you see on the scheme, there are several things here. The first thing would be the turn of the tube, which happens on the border of rain cup and the inlet tube. The second thing would be the flow restriction by inlet filter. The third one would be flow disturbance by water trap. And the fourth one would be another flow restriction by fine particle filter before the entering the sample cell. All these things and tube itself and cell itself of course affect the analyzer. And there are some good effects in there and some bad effects in there. The fast air temperature fluctuations attenuated strongly by the tube. This is a good effect. We don't want fast temperature changes to be present in the cell, because it would imply the need for WebPM learning sensible heat flux term. The non-reactive and non-sticky gases such as CO2 or methane are attenuated very little even in the long tube. This is another good point about this. Water molecule is polarized and it behaves a little sticky. So attenuation of water flux would depend on the tube length, tube diameter, cleanliness and dustiness in the tube, flow rate and humidity. If you pay special attention to properly correcting water flux, this can be good. And in any case, water flux is needed for various corrections and models, so most people have to pay special attention to how water flux is sampled and corrected. The reactive or sticky gases, such as NH4, volatile organic compounds, and so on, are difficult to measure with closed path because of interactions with filters and tube and cell walls. Because of this modification to air sample done by the tube and cell walls, the following four moments become quite important during setup and data processing. Frequency response corrections for tube attenuation are required. They should be individual for CO2 and water fluxes. Such corrections are unique to closed path fast techniques, and we will go in further details with those. The second one is the sensible heat flux portion of WebPM learning term is not needed if the tube is long enough to attenuate the sample temperature. This is also unique to closed path fast techniques, and it's important to remember that WebPM learning term includes three main components: the sensible heat flux component, the latent heat flux component, and the pressure component. Pressure component usually neglected, and for closed paths with long tube, the temperature component should be neglected. And again, we go through this in detail. The latent heat flux portion of WebPM luning density correction for water dilution is still needed, and it should be based on actual slightly attenuated water vapor fluctuations in the cell. Also, it would really be great to have sample temperature and pressure measured inside the cell. Now let's look at all of these key corrections to the closed path data in more detail. First, let's look at frequency response correction. The frequency response corrections refer to family of corrections compensating for the flux losses at different frequencies for a number of reasons. All of these reasons related to instrument and system performance and applied to eddy-covariance technique. The key frequency response corrections are time response corrections, sensor separation, scalar path averaging, tube attenuation, high pass filtering, low pass filtering, sensor response mismatch, and digital sampling. And tube attenuation here, of course, is unique to closed path instruments, because open path instruments do not have intake tube. Again, look at the bottom of the page and note the link, which will give you very detailed description of how these corrections are computed and applied. Frequency response corrections calculated from instantaneous data using co-spectra. Co-spectra is simply a distribution of flux transport by frequency. The transfer functions describe how each sampling problem, such as sensor separation or tube attenuation, would affect ideal co-spectra at each frequency. For closed path analysis specifically, there is a transfer function for tube attenuation. This function helps to compensate for the loss of flux due to the fact that sampling air through the inlet tube attenuates, dampens small fluctuations. It is very strong dampening for temperature, very little dampening for CO2 or methane, and variable, sometimes strong, sometimes weak dampening for water. Frequency response corrections are applied via transfer functions using Kimal-Mohr co-spectral models or actual sensible heat flux co-spectra. When co-spectra is dimensionalized, you can look at sensible heat flux co-spectra and compare it to latent heat flux co-spectra or to CO2 flux co-spectra. This way you can actually use sensible heat flux co-spectra as a correction base for other fluxes. However, co-spectral models of Kimal and Mohr perhaps more advisable because they are tested for a very long time. They have been tested for a very long time, and you don't have to run sensible heat flux co-spectra for every half hour. Kimal-Mohr co-spectra models present a set of equations describing the shape of co-spectra for unstable, stable, and neutral conditions, and they're usually non-dimensionalized, so you have to know your height, measurement height, roughness, and wind speed, and so on. Such conspectral models adjusted using transfer functions at each frequency, and correction factor is computed for the entire co-spectrum. Then you apply all these corrections, including tube attenuation correction for closed path, and when you do it, it can increase fluxes up to 30% or more. And frequency response corrections usually larger at night because you have less turbulence at night. The second big correction used in the closed path and the open path as well is WebPM and luning density term. This term is strictly speaking not a correction because it describes the actual events occurring in the analyzer or outside in the air. However, you have to have this term to get the flux correctly. This term compensates for the effects of fluctuations of temperature for thermal expansion and water vapor for dilution on measured gas fluctuations. One easy way to imagine this process is by considering a surface with actual zero flux and with warming air of constant gas concentration, as you see on the illustration below. As a result, instrument measures flux because of thermal expansion of air parcel and not because actual flux occurs. Again, please see pages 97 and 98 on the link below for more detail. As I mentioned before, the WebPM learning term includes three major terms inside of it. It's dilution term, computed from water vapor density measured in the cell simultaneously with CO2. Thermal expansion term. This term in the closed path instrument with long intake tube is below 1% of ambient and usually neglected. And pressure expansion term, or contraction. It's usually neglected, especially if buffer is used between pump and the sampling cell, so you do not have periodic fluctuations of pressure due to imperfections of the pump. So the bottom equation is the traditional closed path WebPM learning term equation, where you have your initial flux and the term correcting for the water dilution. We talked about the sensible heat or temperature fluctuations being almost fully eliminated in the long tube, and it's important to understand what is long enough to eliminate them. The usual rule of thumb is ratio of 1 to 500 or 1 to 1000 relating tube diameter to the length of the tube. This has been traditionally used by most groups and confirmed experimental studies. Tubes longer than this ratio are not recommended because not much is gained for temperature attenuation anymore, but you might start losing CO2 and water and methane fluxes due to attenuation of fast gas fluctuation in excessively long tubes. It's also difficult to maintain very long tubes clean and free of algae and water and dust. The keeping tube relatively short is especially important when water fluxes are the focus of the study, because water is a somewhat sticky molecule, and water fluxes are affected by the tube more than CO2 or methane or any other gas. All these effects are well known and correctable, but each of them have associated uncertainties. So it would probably be best to optimize the system design from the beginning to make these uncertainties minimal. So how could we optimize the system when we design the eddy-covariance experiment? First of all, we need to make sure that there are no leaks. That's a big one for closed path analyzers, because leaks may lead to alien air entering sample flow, thus corrupting the data. We should also avoid sharp corners in the intake tube. Especially with high flow rates, the sharp turns may lead to difficult to predict flow disturbances, such as standing waves or vortices. We also want to minimize flow restrictions without sacrificing filtering. We can use low restriction filters and use contamination resistant cell designs when possible, so even if some dust gets in, it doesn't affect the reading. And such technology is available and being used. It's also important to have a buffer, the large volume container between pump and the cell. It will help to keep WebPM learning pressure term negligible, and it wouldn't have associated uncertainties if your pressure changes periodically due to the pump. It's important to replace intake tube regularly, especially if it's long, because contamination on tube walls increase flux attenuation. It's also important to avoid extremely high flow rates when possible, because small imperfections of the tube may lead to waves and flow disturbances when flow rate is very high. Another important point is to keep analyzer in climate control box, unless it's specifically designed for outdoors. Independently of the design, principle of operation and manufacture, electronics, optical and other components may and will drift with temperature. That's why climate control box is always a good idea. It's also important to calibrate regularly, because again, independent of method of detection or principle of operation or design of instrument, the electronic, optical and other components may and will drift with time. It would be nice to avoid vacuum when possible, because when sample comes into the cell and expands 5, 10 or 20 times, the fast effects are difficult to predict, and leaks may become a problem with time when experiment is long-term. If water is of main interest, it's important to avoid excessive tube lengths. Even though 1 to 500 and 1 to 1000 is a general rule of thumb, the 3-4 meter is usually sufficient tube length for 1/4 inch or 3/8 of an inch internal diameter tube. Longer tubes may attenuate water without much gain in attenuating temperature. Let's have a few moments dedicated to data processing. The key recommendations for closed path analyzers would be to correct for tube attenuation, sensor separation and path averaging. These are frequency response correction parts of the entire data processing. Then we need to adjust for time delay in the tube. It's probably better to do it via circular correlation. But if you have very stable pump, good buffer, and clean power, you can also do it via flow rate and tube length calculation. So you know exactly how much time it took for your sample to travel through the tube. It's good to use actual core spectra during midday to check if theoretical corrections worked properly. If the Keimal-Moore core spectra and your actual core spectra look generally the same. Your actual core spectra will be slightly below Keimal-Moore core spectra because of frequency losses, and the difference in percent should come out roughly to your frequency response correction. You also need to correct for water dilution, the latent heat flux portion of WebPM learning term, using in-cell latent heat flux, the one which has been partially attenuated. You do not want to use the outside flux, because this is not what your instrument sees in the cell, and this is not how the gas fluctuation is diluted in the cell. It's important to accidentally not correct for thermal expansion, because your tube is long enough and your temperature is attenuated. It's good to check data every few days, because bugs and algae can live and have lived in tubes with 15 to 20 liter per minute flow. So in summary, the main strengths of closed path analyzers are excellent data quality, minimal data loss due to precipitation and icing, minimal uncertainty associated with fast temperature fluctuations, and WebPM learning sensible heat flux term, possibility of outputting mixing ratio and avoiding WebPM learning term, no surface heating issues, automated calibrations, and possibility of climate control of the instrument and the sample flow. And the most important items specific to closed path analyzers are to eliminate temperature fluctuations without dampening gas fluctuations, minimize flow distortion and eliminate leaks, sample air at proper flow rate, which is fast enough for 10 or 20 Hz sampling but not too fast, calibrate and check data periodically. And key processing steps for closed path analyzers are correcting for tube attenuation and time delay, correcting for water dilution using in-cell water data, and not correcting for thermal expansion when long intake tubes are used. Now let's talk about something new in this open path, closed path business, which is coming from LI-COR this year. Knowing both open path principles described by Lu Kong and closed path principles described here, we have developed the new instrument. We have united strengths and minimized weaknesses of closed path and open path analyzer design in a new design. This is not exactly the open path analyzer, and it doesn't have to be exactly traditional closed path analyzer. It's a compact enclosed gas analyzer enabled for operations with short intake tubes. It has strengths similar to closed path analyzers, such as minimal data loss due to precipitation and icing, no surface heating issues, improved water specifications due to absence of solar filter. It also has strengths similar to open path analyzers, such as small easily correctable flux attenuation loss in short intake, infrequent calibration requirements, minimum maintenance requirements, low power configuration when used with short intake tube, small size, lightweight, and weatherproof design. It basically gives you all the advantages of LI-7500 and LI-7000 or LI-6262 in one instrument. For detail on this design, please see our webpage at the link here, and you could also register for LI-7200 webinar at another link here. And here is the picture of this instrument deployed in Canada, in the Vancouver Island. Thank you very much.
Now we are going to transition into our live question and answer session. Most of you have been submitting questions along the way during the presentation, so thank you. If your question isn't addressed during this live Q&A, a panelist has either already gotten back to you or will get back to you as soon as possible. For those of you who haven't submitted your question yet, you can send them to us by expanding the questions panel in the control panel window and typing into the dialog box in the panel, then clicking the send button. Alright, I think we're ready to go with questions here. It looks like our first question is for George, and it is, how often do you have to calibrate closed path instruments?
The closed path instruments, of course, different from each other and depends on conditions at the site and how well they are climate controlled and what's the underlying principle of operation. For most of the closed path analyzers used for eddy-covariance operations, people calibrate them daily or weekly, somewhere in between. People who are interested in high precision mean concentration to compute fluxes using inversion models or just for general modeling sometimes calibrate hourly. And people who are positioned at the remote sites or do not have infrastructure to bring calibration cylinders to the sites calibrate monthly or bi-monthly.
Great, thank you, George. It looks like our next question is for you as well, and this participant asks, George said the LI-7200 is enabled for short intake tubes. How short?
We run 7200 in our field tests with 4-meter tube, 1.5-meter tube, 1-meter long tube, 90 centimeters, 50 centimeters, 40 centimeters, and no tube. And in all cases it provides the correct flux. So it gives you a lot of flexibility. I wouldn't suggest using it for eddy-covariance without tube, because you have to bring the sensor head very close to the sonic anemometer. Optimum tube length we figured out theoretically and in experiments is between 50 centimeters and 1 meter. This way you attenuate most of the temperature and you almost do not attenuate CO2 and water. And whatever you didn't attenuate in temperature, you measure directly in the cell. But that would be for the next seminar on 7200.
Great, thank you. It looks like our next question is for Lukong. Lukong, any news regarding the LI-COR open-path CO2 H2O analyzer?
We introduced that open-path 7500 analyzer in 1999. It quickly became a standard analyzer on the flux tower around the world. with all the experience and expertise we get from the past 10 years, LI-COR is introducing a new generation of the OpenPath CO2 and H2O analyzer. We call the 7500A. It has lots of new features. One of them is you can change the chop mode housing temperature to be either at 30 degrees C or 5 degrees C, depend on the ambient temperature. This way you can reduce the power consumption in the cold weather. It also has data logging capability. You can synchronize and record the sonic wind speed data and the CO2 data with this new analyzer. It has many options of data output, including Ethernet, SDM, serial, and analog. See our website, and we have more information.
Thank you. It looks like our next question is for George. How much power does it take to provide proper flow rate to the LI-7200?
The LI-7200 is different from most of the traditional closed path analyzers. It doesn't have to have fine particle filter because it uses same principles and optics of 7500, which is fairly insensitive to dirt. It normalizes the dirt out of there, so you're still measuring correct concentration and flux even when your windows or cell walls, in case of the closed path, are dusty. Because of that, and because your tube is short, you can provide, let's say, 15 liter per minute flow, which is plenty, with the 15 watt flow module. And this flow module is available from LI-COR for people who do not have their own pumps. And this flow module is designed for the solar power operation. It gives you 15 liters per minute with 15 watts. It uses precision mass flow controller, and it's fully controlled remotely using Ethernet. You can also use the fan instead of the this flow module. With the fan, theoretically you can get to maybe 7 watts, and this is described in Egg Forest Meteorology paper by Clement, Burba and Griele from 2008, I believe. We used several designs, and some of us use fans and some of us use pumps in different configurations.
Great, thank you. It looks like that's going to have to be our last live question. I want to take a moment to thank the participants for their questions and to remind them that if their question hasn't been answered, to stick around for just a little bit. Our panelists will get back to you as soon as they can.